It is a pleasure to introduce Professor Alain Yger from Bordeaux University, who will discuss integral representation formula and residue calculus with applications to interpolation. So please, Alain.
Okay, well, thank you, Daniel. And well, also thanks to all the organizers of this conference in Chapman, and just many of them are my friends, my collaborators, and just Daniele Strupa, Daniel, Ahmed Sebar, Irene, just Mihaela, Kai Vogel, and so many. And it's always a pleasure to be there in Chapman, even if today it is virtually. And I must say that it is the second time, it is my second IOTA conference. The first one was in 2000 in Bordeaux. I think it is the first time I met Daniel, and just, so really time is going, and just, well, I'm a bit afraid to be somehow some kind of stranger in the community, in the IOTA community, and then I hesitate really what to tell you about. I wrote this abstract, but I realized that then it was too ambitious to try to explain to you so many things in such a short time. So in fact, I prefer to stick to some recent developments and especially focus on things which were related to, especially to my discussions with Daniel and my collaboration with him, and also the questions which remain still unanswered that Nikolai Nikolsky asked me for many years about how to use all these techniques to operator theory, and just so this is a dream, but I still keep in mind this dream. So just well, of course, it's just, and my discussions with Daniel, through him, I learned many things about interpolation, about modelization of non-stationarity, and maybe from this, I hope that some ideas will come through. And just well, so just I will try to explain to you things about. Very few things about residue calculus, a few things that could be of interest in, well, in relation with operator problem. Although commutativity, of course, is always there, and just which is a big stumbling block. But nevertheless, let's try. So just there is a notion, a word that maybe you don't know so well, which is a word of quasi-regularity, but I'm pretty sure that everybody knows what it means. And just, you know that, you certainly know that when you have an interpolation problem, things are always easier. In fact, they are even, it could be extremely difficult in the other case. Things are always easier if the set that you define by equations has exactly the same codimension than the number of equations you use to define it. For example, when you want to define points, you use an equation, and just and of course in this generalizes the setting of hypersurfaces. See, just if for example, if you have a finite number of points, let's say in Cn, that means usually it's impossible to define them by an equation, and just to define this zero set by an equation. You can do it locally, but you cannot do it globally. And this is quite a problem with respect to interpolation questions, and just and especially in relation with integral representation formula. So this is phrased differently in algebraic terms. If you take a commutative ring, so this makes sense only in the commutative ring, a sequence is quasi-regular if, in fact, some people would tell you the Kosul complex is exact at any step except the step equals 0. But the way I wrote it here is some kind of asymptotic. I wanted to focus on the fact that it is some kind of asymptotic condition. You see, for any integer, Each time you have a formal relation with coefficient in the ring, and which has total degree n, which lies in the ideal power n plus 1, it means that the coefficients have to be in the ideal. And when the sequence is like that, it is called quasi-regular. And it is a nice setting to do many things in in relation with Taylor developments, residue calculus, and a lot of things. So this notion of quasi-regularity is really an important notion. Of course, if you take a family in general, it's not quasi-regular, and that just except if it is reduced to singleton, to one element. But otherwise, quasi-regularity is well, intuitively, if you think about the AK are functions, then or polynomial, for example, or anything these holomorphic functions, then it means that it is equivalent to say that the zero set they define has the same codimension than the number of functions you take. This is just this is exactly another alternative way to phrase quasi-regularity. But it's not an easy notion from the algebraic point of view, but you see, because you see, it is asymptotic. You have to write that for NaN, you have such things. And so it's not, it's a little heavy. It's not completely immediate to translate it in algebraic terms. So let's assume we take such a sequence. I'm going to explain to you briefly how from this kind of sequence, you get traces that will be the bricks, the basic brick to build residue calculus. In the complete algebraic setting, for the moment, it's completely algebraic. I keep to the algebraic setting because I want to be as algebraic as I can, and just. So usually the ring is, the commutative ring is a B algebra. It is an algebra over some ring that I would call a ring of coefficients. You see, just there is a ring of coefficients, and you have an algebra over this ring of coefficients, and just you put everything in situation that you are able to define a notion of trace, which is something fundamental. And residues are traces of operators. So in fact, in order to do that, you assume that this quotient here, when you take the quotient of A by the ideal, then it is a quotient module, a quotient B modules, and you make the assumption that it is finitely generated and projective. So just let's, for example, in the classical situation where B is a vector space, and then it's a finite dimensional vector space, and in this situation, you all know that you have a trace, and just any homomorphism from P to P as a trace. But there could be situation, especially in the situation we were discussing with Daniel, where we really need to work over a ring and not over a field, and even a ring which is not an integral ring, a ring which may have divisors of zero, which is a problem. So here the situation is the most algebraic that it could be, the most formal that it could be. So once you have such a situation, you see, you are able to have a trace. Something which is extremely important is that once you have a sequence which is quasi-regular like that, you are able to develop formally along the powers of the element A. You are able to develop just any element in the algebra A. And the development is, of course, the coefficients here depend on the choice of a particular linear section for the quotient. You see, a map sigma, which is bilinear, and which is, when you compose it with the projection map, you get the identity. So it goes from the quotient to A, and when you come back with a projection, you get the identity. This is called a section. And once you have a section, it's a very simple exercise to check that when you take R here, it can be expanded. And these elements here, you see, these elements here, which are in the quotient, are uniquely determined once the section is fixed. And of course, if you change the section, you find other elements. So, but these elements are unique. And it's really an important fact. You see, once the section is fixed, you have some kind of development. And just and take another section, you will have another development. But the elements which are here are unique once the section is chosen. So that's the beginning, essentially, of everything. Because now you can do a little more than that. If you take two elements, you see, in A, and if you form the product, you develop the product, and then you realize that there are associated to R, there are unique operators here, which are operators from the quotient to itself, such that for any R prime, the unique element that you had before is just the action of this operator on R prime. Of course, this list of operators depend on the choice of the section and depend on R. And just so here comes the non-commutativity, and just because you have transformed your problem into, you have associated to any element R, but basically not to R, but to the operator, the multiplication by R. You have associated to it a list of operators, you see, in the series of formal power series with coefficients operators. And now this formal power series, you are going to manipulate them, and you manipulate them in a complete non-commutative way. You construct a Jacobian determinant, you see, you differentiate each formal power series with respect to A1, A2, AK, AN. You form the determinant. Of course, it's a terrible thing because it is non-commutative, and just you expand the determinant by the classical Sarus rule, and it's an horrible expression. You multiply by H, and you obtain, when you do that, you obtain still a formal power series with coefficients operators. And in fact, the trace of each of these operators, you see, does not depend on the section. And it is an object, which is precisely the residue corresponding to the power A1 with exponent kappa 1, the power kappa 1 plus 1, kappa n plus 1. And this formula here is nothing else than some kind of, at least it is a Taylor formula, if you take the trace of both sides, you see, let's say. If you take the trace of both sides, it is some Taylor trace formula. You identify the traces and you get what could be an algebraic version of the Taylor formula. And just so this is, well, I want to insist on that because you see, residue symbols are not defined one by one. They are defined all together as a list. It is the Taylor series which is defined. It's not the residue symbol. So in fact, most of the problems related to interpolation, well, should involve the whole list of symbols for any powers, and just because they are defined as a family, and just all this construction, it is a Taylor series that you define. It's not, well, it's not, I will come back to this situation before. You know that in the Taylor series, there are also factorial as a denominator, and just so these are not differentiation, they really are residues. Just so that's really the formal, well, expressed in concrete terms, it is the formal introduction to algebraic residue calculus. But if you try to read a book written by algebraists, for example, Lippmann and book like that, it would be impossible to understand anything because it's not everything is written in a kind of coded way, and it's very hard to extract the essential substance. But here it is. You see, it's just, well, the important thing is this idea of the fact that residues are traces of operators, and the fact that their computation involves non-commutativity because it involves this multiplication of series of operators. You see, that just that's a construction which is formal, but of course it fits the residue that you know in the residue theory that you know in complex and multivariate complex analysis enters within this frame. Just it's a particular case of this algebraic frame. So there is something which governs completely residues. Well, residue calculus, it is something that the algebraists call the Weber's lemma, but people in analysis prefer to call it the transformation law. And something extremely convenient. I'm just going to formulate it in as Leibniz would have formulated. That is residues. I will not relate residues, but I will relate residues multiplied by factorial. And you know that this is the derivative. And in fact, when you take two sequences, A1, AN, and A tilde 1, A tilde N, which are related by this relation, you see A tilde is obtained by multiplication of the sequence A1, AK by a matrix of elements in A. And you make the assumption that the two quotient modules here remain finitely generated and projective. Then you have this nice way of here, when you multiply by factorial k, it is reasonable to denote this d over dA power k of this differential form. You see, it makes sense because residues, you know that the residue is the derivative at the order k divided by factorial k. So, but of course, this makes sense only if the ring is an integral domain with characteristic 0, because otherwise I cannot make division. But if you are in this situation, for example, if B is a field with characteristic 0, then you can formulate the transformation law within the words of Leibniz. And in this case, in fact, it is much more understandable. It is essentially Leibniz differential calculus. In fact, so residue calculus is connected with Leibniz differential calculus, except that you have this division by factorial, and just which we will see later on that it's not. It is important, and just it's really an important fact. This sequence factorial k. Well, in fact, when I say factorial here, it's a product of factorial k1, factorial kn, and just I took abridged notation in order not to take too complicated notation. I'll look at the time and just that's okay. So let's so this is formulation with the transformation law, which it governs essentially it governs it rules completely residue calculus. And now let's come to complex analysis and to something which will approach the polydisk in CN, and just what is a Weil polyhedron in CN? Well, basically it is something like the polydisk, except that the number of function is not equal to the dimension, not equal to n. So you may have more function than than the dimension. So when you have you can take as function the coordinates, and in this case you recover the polydisk. And a Weil polyhedron is a box like this. Fg strictly smaller than ρ1, F1 strictly smaller than ρ1, F2 strictly smaller than ρ2, etc. Fm strictly smaller than ρm. The important fact is that it has to be relatively compact in U. And this is really the point. And just we will see some examples just with inner function in the polydisk later on, where it is not the case. In fact, the polydisk is a Weil polyhedron for the coordinates or for Blaschke products in one variable, univariate Blaschke product in one variable separately, one Blaschke product in Z1, one Blaschke product in Z2, in Zn. But, well, that's, if you say that the polydisk is a Weil polyhedron, it is only true for Blaschke product, the configuration of Blaschke product in single variables, you see. Otherwise, it is not. So this is the main point here, is that there are more functions, there could be more functions than the dimension, and just and there is some condition which ensure that the boundary, not the boundary, but what we call the Shilov boundary, which is a small piece of the boundary, but like the poly circle is for the polydisk. You see, it's something which is n-dimensional, and it is the same here. It is not the boundary, it is a Shilov boundary. It has to be smooth in order that you can integrate on it. So that's Weil polyhedron. And then you know that since I took here a pseudo-convex open subset in Cn, you can solve in it the Gleason problem, and you have a Gleason formula. And, well, in operator you call them Gleason formula. In complex analysis we call them FR formula, but it is essentially the same. And just you can solve Gleason problem. And once you have a solution for the Gleason, which is not unique, of course, it's just except when n equal 1, but otherwise there is no unicity. Once you have a solution for the Gleason problem, then you have a Cauchy formula. Well, Cauchy formula, except that it's when m is strictly bigger than n, this formula is completely rigid. It is a representation formula inside the polydisk, but you cannot deform it. You cannot shrink. You cannot shrink, for example, the integral towards the set of common zeros. So it cannot be used as an interpolation formula. And as soon as m is strictly bigger than n, well, it's very hard to. This formula is, well, it was something very which looked very important at the beginning when Weil discovered it, and then people realized that what it could be useful for. It's not clear how to use such a rigid formula, since you cannot deform it. Why you cannot deform it? Because the sigma j here, you see, are not cycles. They are pieces of cycle, but not cycles. So in fact, deformation is not possible. You can use this formula to make expansion along the powers of the Fg. You see, this, of course, you know how to do. You develop the Cauchy kernel as a power series, and then it is a standard trick that you all know in Cauchy formula. See that just and then and this kind of development is what is called a Bergman-Weil development. You see, it's not formal this time. It's an explicit development of f along the powers of the Fg, but since these coefficients here cannot be deformed as a residue in the case where m equal n, then you can deform this thing and they shrink to the set of common zero. Here they do not. You have to keep them as they are, and the formula is as it is. So this is, but I wanted to formulate the Cauchy formula in the most general setting, since I will use it, I will show how to use it to derive interpolation later on in this talk. And just, so this is really the form of Weil formula in its generality, Cauchy-Weil formula in its generality. So in the case where m equal n, then situation is very nice in this case, because the coefficients, this boundary integral shrink exactly like Cauchy, the usual Cauchy integral, and just and they shrink. You can deform the polyhedron to be close to the zero, and the coefficient is just. In fact, it is a local residue. Which corresponds you see delta has completely disappeared. It is a residue corresponding to so basically it is a sum of the action of differential operators on the form which is there, the coefficient of the form which is there, and then you evaluate at the common zero. So you have it's really the right-hand side here is really an interpolation series, and just that if you replace h by a germ of a function near the zero, you find interpolation. You get interpolation. So this is really what it's difficult to separate the names of Jacobi, Kronecker, and Lagrange, but this is really the Jacobi, Kronecker, Lagrange trace formula, and that just written here in its expanded way. And well, in the case where m equal n equal 1, in the algebraic setting, this formula is just nothing but a reformulation in the univariate case. It is a reformulation of the iterated Euclidean division. Well, this is almost immediate to check, and just when you do the Euclidean division by f, you iterate it, and then you obtain it's exactly the same thing that to write this Jacobi, Kronecker, Lagrange trace formula. Why do I say that? Because I just want to make a slight remark for the first time about this the thing which I learned from Daniel, and just there are non-commutative situations which are skew situations introduced by Orr in the 40s, a very long time ago. Orr calculus, which is in fact you take a field which is of course commutative, and you have a variable z, and you have an automorphism. You see, it's not Cz when you have a coefficient. Cz is equal to z, and the action of sigma on the coefficient. For example, if you take in the situation where you try to modelize, as Daniel was trying to do in the 90s, you try to modelize non-stationarity, discrete non-stationarity, then it's exactly the configuration you have is exactly the configuration of Orr calculus. You have, and Z is the shift, Z star in the adjoint, and the automorphism here is Z star CZ. Just unfortunately, it's not a field. You do not work over a field. You work over a ring, which is not even an integral domain. So there are serious problems related to that. So it's not a field. It is not an integral domain. Because it is the ring of coefficients is the ring of diagonal matrices, and of course diagonal matrices which are non-zero coefficients is non-invertible, and just so in fact it's just you don't have any. You have of course plenty of divisors of zero, so it's a bad ring. But nevertheless, it is the configuration of Orr calculus. And in this configuration, of course, over a field. Then there is also Euclidean division. There is a concept of resultant. This has been done, for example, by, I found this reference by Eric in the 280s, but there are certainly other references. It is related to Dieudonné determinant. And of course, it's possible to revisit. It's possible, and this is what we hope to do. We hope to revisit the approach of Daniel, which I will describe later on in the classical H2 of the n setting. But it was a remark to tell you that in some cases, non-commutativity can appear, especially in the case of skew field. You see, this is a situation which is peculiar, but it's interesting in relation with operator theory. It could be interesting with respect to operator theory and to at least to signal analysis and to modelize non-stationarity, discrete non-stationarity, and just so something which is, of course, a big success of Jacobi, Kronecker, Lagrange's formula is that it produces a closed formula to solve Hilbert's Nullstellensatz. So really, it's a corona problem. The most well-known corona problem, Hilbert's Nullstellensatz, which resumes to solving Bézout identity. You take n+1 polynomial without common zero, basically. More than that, here you assume that the algebraic hypersurfaces intersect properly in Cn. So each time you take k of them, the codimension has to be n minus k. So when you take n+1, of course, the codimension has to be empty. But this is you assume you put them in nice position, and of course in this case you have. But it is trivial. You have a Gleason relation, algebraic Gleason relation, which are completely algebraic and completely immediate. And well, you introduce, it's a little technical, I will not insist so much about that. It was this kind of result appeared in a very primitive way many years ago in the 90s when it was the beginning of my work with Carlos Berenstein, and it started my collaboration with the algebraist and from there, and just but now we can formulate it in a more direct way, and we understand it better, and just and then you see you have the possibility you formulate it as a parametric version of Hilbert Nullstellensatz. Then you have to fix the parameters, and you solve if you fix the parameters, you will solve the Bézout identity since the parameters are generic. So in fact, you choose parameters, and then you construct Gleason functions for not the polynomial, but the polynomials multiplied by an expression where the parameters are, and then surprisingly, you solve the corona problem. You see, in a beautiful closed formula, and just that if you fix the parameters are generic, and if you fix them generically, then you solve the Nullstellensatz on any field, any subfield of C, at least in characteristic 0, but this works in any characteristic. So in fact, it's now there are several questions about that. Well, one of the most not anecdotic but interesting question is, of course, you know that solving Hilbert Nullstellensatz is something capital, because this Hilbert, the Nullstellensatz decision problem is NP complete, and if it was P complete, then the conjecture P equal NP would be true over C, which is equivalent to say that it would be true over Q bar. This was a theorem by Schub and Smale in the 90s. But what Schub and Smale show is that proving that the sequence factorial k, you know, remember this sequence factorial k that we saw a long time ago, proving that this sequence is ultimately hard to compute would be enough to disprove P equal NP over Q bar. hence P equal NP over C. So it could be interesting to see that this sequence factorial K is precisely the sequence which connects Leibniz calculus with multivariate calculus, residue calculus. See, these residues are derivative divided by factorial K. And that's, of course, a closed formula is not an algorithm. So there is no way to exploit, it's a closed formula, but from a closed formula, you cannot derive an algorithm. And just that's another, this completely another direction. But nevertheless, it's just, if everything could be done algorithmically and not by a closed formula, then this is what we have been in the last years. We have been working a lot with Martin Sombra to analyze the complexity, the arithmetic complexity of residue symbols. And since these residue symbols today are extremely used also by physicists in Feynman diagrams. You see, they need to compute multivariate residues. And I receive a lot of mail by physicists who ask me each time how to compute, they can use such formula to compute their residue symbol. So, in fact, it's there is a residue calculus is also important for physicists. Total sum of residues, which is not local residue, but total sum of residues. So here is the simplest corona problem. You see, just I look at my watch. Well, let's go on now. Let's come to my one result of my discussions with Daniel, and just and look at the problem in the polydisk. You see, still with m equal n, and just still with m equal n. Look at the polydisk, and in fact, consider this is something we had the idea to look at a few years ago. You consider a system of inner rational function. You see, like in Rodin constructions, and P1 over Q1, Pn over Qn, and just they are inner function, and then you put you add some. So when you have such a system of inner function, it's very easy to see that you can solve the Gleason problem in an ad hoc way. You can solve the Gleason problem exactly like I explained here. You see, by trigonometry, by polynomial identities of this form, keeping the Hermitian symmetry, and it's not difficult to do that. And just so there is a peculiar way to solve a Gleason problem in this case, and just because of this relation between there is a P which is there is a Q which is a P somewhere, and there is a mistake in my slide here. QG is ZG, PG is not PG repeated 2 times. It's QG, QG equal, etc. Just sorry for this. I just realized. Now, once you have this, it was tempting to try to introduce some Suragler type class, which fits precisely with the Cauchy-Weil formula. You see, and what does it mean? It means that first you impose that P the n, here you have exactly n function, n inner function, you see. This n inner function define a finite zero set. And just so basically because they do not, the zero set does not hit the real boundary of the polydisk. So that just, so it's a finite zero set inside. Some condition also over 1 over the product of Q1, Qn, that it has to be in L2 of the Shilov boundary. That's and mostly the most important thing is that if you want to mimic, to exploit Cauchy-Weil formula and to profit from it, then you have to be able to choose a particular solution for this Gleason problem here. so that the determinant can be expressed as a sum of the determinant which has the Hermitian symmetry is positive, in fact, is the sum of L of W, L of Z bar. This is exactly like in the Fouragler presentation when you are working with one function. Here it is n inner function in n variables, so see, but of course which are not Blasch product in separate variables, and just this was really all the difficulty, and just we wanted to escape to the situation, to the univariate situation, and just and look at the interpolation questions in this setting. And this is precisely the result, one of the results that we could get precisely with Daniel, and just that something that, of course, if the polydisk is not a Weil polyhedron for the system of inner function. If it was, it would mean that the inner function would be in separate variables, Z1, Z2, Zn, and we are not interested in that because we want to escape that. So you have to enter in it to find a Weil polyhedron. So you have to shrink the polydisk in order to get a Weil polyhedron and to be able to exploit Cauchy-Weil formula. See, you cannot use Cauchy-Weil formula in the polydisk. You can use it for the coordinates, but you cannot use it for a system of inner function. So you have to shrink inside. Nevertheless, you are able to, in the shrinked polyhedron, you are able to represent and to introduce a continuous operator from H2 to H2 of the n power m. M is the number of L, and which appear in the Fouragler expression. And you are able to write H precisely with this L over Q, which are in H2. And here you have something which is in H over 2 of the n, but which is evaluated, which is tested against phi over rho. Rho is the multiradius of the polyhedron delta. So this is, well, it's really the first time that, well, we never saw in the literature a combination of Cauchy-Weil formula with the Fouragler. Since my work with Daniel, now I heard from, I was giving a conference also by internet in Sochi with all these Russian people. And in the school in Krasnoyarsk, there are now people who are working on our paper with Daniel, and we are trying to at least to see what could be done in this direction. So, so these things, in a strange way, this kind of idea were not used before. Just Cauchy-Weil formula was in the world of multivariate complex analysis. Just, but not, and of course you can continue in this case, and you can really build a Lagrange interpolator at any level, and formulate, keeping in mind norms, and formulate Lagrange interpolation problems. Especially formulate them, as Daniel likes a lot, in a non-standard way. So this is basically all the content of this this approach that we had with Daniel about just this trying to make the Cauchy-Weil formula enter in classical things about the politics. Again, our main goal was to be able to deal with with zero set, which were not Cartesian products. This was basically, it was basically the motivation. Now, I should say to finish, it's almost, well, I need to, these are really my last slide. I will try to explain something a little more involved, what we are trying to do with what we have, another recent paper that, another recent thing that we are doing with my friend Alekos Vidras, precisely to try to modify Cauchy-Weil formula in the case where m is strictly bigger than n, which is not exploitable. As I told you, it was not exploitable as it was because it's a rigid formula. You can do nothing with it. How to modify it into an interpolation formula, and that's so I start with a Weil polyhedra and I fix a threshold n, fix once and I start with my Cauchy-Weil formula, this rigid Cauchy-Weil formula as it was. Just you see this inside the polydisk, you represent like this. Since m is bigger than n, it is rigid. You cannot deform it, and you cannot use. This is not even if you make the expansion of the geometric of the kernel here in geometric series, it will not provide an interpolation result, and just because you cannot deform the integral, and just so let's start with this thing. Nevertheless, you can cut it. You can cut the Bergman development, you see, and you cut it at not an n plus n. I will explain in a while why you have to shift the threshold and just and you shift it. And of course, what remains, you can profit from this formula. What remains can be written in many ways, explicitly in the ideal generated by the F kappa here, with kernels which are completely explicit. This is exactly what you do with Lagrange interpolation formula. You can, it's not unique. You have several ways to exploit. You see, the formula is written in this form, and you have several manipulations in order to express. Once you isolate the principal part here, you have several ways to express express the remainder part in the ideal power n plus n, and just because the thing here is of degree n plus n minus 1 at most. Why n plus n? Well, this comes from well, this is I never knew why this result was completely fascinating Nikolai Nikolsky, and he always asked me about this problem many times. I heard him listening, especially when he was working on the apparent spectrum. He was always he was claiming that Briançon-Skoda's theorem was absolutely fundamental. Well, it is a strange result. Basically, it tells you that if you have a function h, which is holomorphic in the polydisk, yeah, not in the polydisk, in the Weil polyhedron, but it's nothing. You can take any domain in Cn. It's not important. It's a local problem. If you divide it by the maximum of all module of F kappa, when kappa equal n plus n, so you have to increase here. Increase, but only by something which depends only on the dimension, just by n. And if this is bounded, then this implies that h is in the ideal power n plus 1. You see, the gap, the difference is n minus 1. You have to put this, to make this hypothesis, and this is very, usually it's very hard to check that something is in an ideal. But in analytic terms, it is much easier to show that this quotient is locally bounded. And so this is why this theorem is so important. And this is the reason why I shifted here. I truncated my Bergman-Weil development at the level n plus n and not at the level n, in order to use this later on and to transform my formula, my Cauchy-Weil, my bad Cauchy-Weil formula here into well, some kind of formula that could be used for interpolation. So let's do that, and just and in fact, you see, this is just it's a bit technical, but this is basically the theorem that we got with, well, last year. It appeared last year, but it was this paper was done some years ago. It took time for the referee, and just but in fact it tells you that basically you you know that there was this part when if I come back before in here, there was this part here which was a false Lagrange interpolator. You see, because integral were rigid, and of course here is something which is in the ideal starting at the power n plus n, the ideal power n plus 1 n. So the key point is to transform this false Lagrange interpolator into a true Lagrange interpolator, and this is precisely what we were able to do here. You see, this false Lagrange interpolator differs by this kind of object, and this is a true, in some sense, it's a true Lagrange interpolator, except that it's not. You need to put this analytic condition to be sure that it kills the current that appears there. You see, it's not. There is still this this shift by n and n minus 1, which makes this, basically this formula is obtained by an average of formulas which correspond to the regular case, the case where the number of function is equal to the dimension. And there is a very important formula in complex analysis, which is Crofton's formula, which is a formula that goes back to the 19th century, which is extremely useful in such an approach. So this was really the theorem with Vidras, and I will conclude with this theorem. I just put here just a few references to, well, maybe to the recent. No, that's just. Let's come back to this. There is this thing which I don't know how to eliminate. So there is this. It should be. You can put it there and just. So this work with Vidras appeared in Material last year, and this also my work with Sombra, and just to study the complexity of residue symbol, which is something extremely important both for algebras but also for physicists, because it governs everything from the apparently. Well, just. One thing which I forgot to mention about this Nullstellensatz is what the main question is: could it be possible that people like Kelly, Kronecker knew about these things? And there is a strange book of the beginning of the century in 1900, and just which book by Netto. Eugène Netto, which is called Algebra, where there were some results of this kind, of course with no proofs and no really hypothesis. So you don't know what were the hypotheses, and there is no proof. But there could be some hint that Kelly or Kronecker, all these people which manipulate Kronecker interpolation knew about such things more than 100 years ago. And then my work with Daniel and this thing about the Cauchy-Weil formula, and some older work where we started some years ago just about this idea of non-standard interpolation problem. And well, also, but I had no time to speak about these things because to tell you really about currents and just that this is all the things which are behind, especially the use of Crofton's formula in the work with. I work with the people in Sweden, and just which now is now completed and all appeared. And there is this survey paper in which I wrote, and it's also mainly this monography that we added the name of Berenstein because we started to do that more than 10 years ago, and just this monography now is finished, and I have to send it. I was waiting the end of the week because I told. Inamet in the IMS that I could not work this week, so I sent the manuscript to the editor, and it should be about 500 pages. But it's really everything, all what has been done in multivariate residue calculus from our old book in 1993 in Birkhauser, and just of course this story is things that
Alain,
progressed a lot.
I think
So I stop here.
Thank you very much.
Thank you. And just
is there time for a quick question from the audience or from online? I have to share a session in 5 minutes. This is why I'm saying this, a quick question.
I can stop sharing files.
But a quick question, there will be time, of course. Otherwise, so let's thank Alain again.
Yeah.